Hello everyone, and welcome to the channel. In this video, we'll take a look at the ready pin of the CPU, how it can be used to stop the CPU during DMA access or to access slow devices, and we'll take a look at the modifications that we have to make to our data bus demultiplexing circuit in order to support these use cases. I hope you enjoy! In the past two videos, we discussed the bus enable pin and how we could use it to prevent bus contention when doing DMA access. And at the end of episode 3, I discussed how we couldn't really use bus enable without stopping the CPU because it only impacts the output buffers, and the CPU will continue running with its buffers disabled. And so I mentioned that there was two ways we could stop the CPU, the first one being reset, but that's not really useful if every time you do DMA access, you have to restart your program. So there is another way you could stop the CPU, and that's by using the ready pin. If we look at the block diagram of the CPU, you can see that the ready pin is connected to the timing controller, and so it will actually control the behavior of the CPU as it relates to the clock. So let's see what the datasheet has to say about the ready pin. So if you look at the datasheet for the ready pin, it says that ready is a bidirectional signal. When it is an output, it indicates that a wait for interrupt instruction has been executed, halting operation of the microprocessor. A low input logic level will halt the microprocessor in its current state, and returning ready to the active high state releases the microprocessor to continue processing. So what does that mean? Well, the ready pin is bidirectional, which means that it can be driven by the CPU or it can be driven externally. When it's driven by the CPU, it means that the wait for interrupt instruction has been executed. So what is the wait for interrupt instruction? If you look at the description of the wait for interrupt instruction, it says that it pulls ready low and places the processor in the wait for interrupt low power mode. An interrupt or reset will terminate the wait condition and transfer control to the interrupt handler routine. The way you would use this is if you wanted to save power, for example, if you're running your CPU from a battery, and you wanted to go into low power mode until you have some kind of input via an interrupt. So you would execute the wait for interrupt instruction, and then as soon as an interrupt or reset happens, the CPU will start processing the interrupt. Okay, so I'm not going to go into more detail on how to use the wait instruction, but what matters to us today is that when you execute it, the CPU pulls ready low. And so that's how the ready pin can become an output. Outside of the wait for interrupt instruction, it's always an input. And so you can drive it low in order to hold the microprocessor in its current state. As a first step towards using the ready pin, it would be nice to be able to remove that complexity and have only unidirectional signals. So I want to see if I can demultiplex it into two pins. One which would be the wait output, and one which would be the ready input. So it's something that Western Design Center has thought about, because if you look into the description of the hardcore model, which is what you would use if you wanted to integrate the CPU into your own IC and license the IP from WDC, it mentions that the only functional difference between the physical CPU and the core is the ready pin. In the CPU, the ready pin is bidirectional, utilizing an active pull-up. But in the core, the ready function is split into two pins, ready in and wait. And the wait output goes low when the wait for interrupt instruction is executed. So I want to try to replicate this in my circuit. This way, each pin will be easier to reason about. Let's try to model what the pin looks like inside the CPU, and then we can see if we can extract this information. So from looking at the datasheet, this is a conceptual representation of how the ready pin looks inside a CPU. So when you're not in a wait state, the ready pin is connected to 5 volt through an active pull-up. This pull-up can be turned off, which is what's mentioned here in the datasheet. The ready pin has an active pull-up, and when outputting a low level, the pull-up is turned off to reduce power. And then this goes towards the internals of the CPU as the ready input. So what you set on the input of the ready pin is transferred directly to the CPU. And then when you execute the wait for interrupt instruction, wait goes to 1, and then this is driven directly to ground. So ready goes low and it becomes an output. And then the pull-up is turned off. So this is a conceptual representation of how I think the pin could work inside the CPU, but it will help us reason about how we can extract both the wait and the RDYIN pin in our circuit. Okay, if we go back to the data sheet, we can see this statement at the end that says that the ready pin can be wired ORed. This is an indication that the gate of the CPU is actually open collector. If you look into the Wikipedia page for open collector, you can see that it's an output that behaves like a switch that is either connected to ground or disconnected. That's almost what I've drawn here. You can see I have a switch here that can be connected to ground or connected to a pull-up resistor. And so I guess the output is similar to an open collector gate with an internal pull-up resistor. And so it should be pretty easy to combine this pin with other ICs using wide logic connections. That's a way to implement logic functions with either open collector gates or diodes. So another way to think about our conceptual ready pin input-output circuit is to replace a switch with a diode. And that's what I've done here. You can see in this case with wait being disabled that there's no current flowing through this diode because everything is connected to 5 volts. And so the ready pin is pulled up. So ready is 1. And when wait is active, this is pulled to ground, and so current can flow through the diode. And so this is pulled down, and then ready is 0. And so this is a circuit pretty similar to the one we see on the wired logic connection page. And so let's think about how we want to combine our wait signal with our ready pin to be the CPU input. This is the truth table of our circuit. We have the wait output of the CPU here, our ready input that we want to combine, and what should be sent to the CPU over the ready pin. When the wait signal is low, it's an active low. So we're in a wait state when it is 0, and so in that state, the CPU should be stopped. When wait is 1, then we can ignore it. And then when ready in is 0, we also want to stop the CPU. And when ready in is high, then we want to let the CPU run. So this is how we can combine our inputs. As you can see, ready is the end of wait and ready in. And so we need to build a wired AND connection. That's the circuit over here. And so if you notice, we already have part of the circuit completed. We already have the pull-up resistor. We already have one input with a diode that is internal to the CPU. And we have the output, which is the ready pin, and we only need to add the ready in input with a diode. So let's take a look at that. So this is the updated circuit with the additional diode and input for ready. You can see that when ready in is high and wait in is high, everything is connected to 5 volts, and so the ready pin is high. Now if I bring either ready in low or wait in low, then the ready pin goes low, and if both are low, then the ready pin still is low. So that's correct. So we have successfully made the RDYIN pin unidirectional. We can drive it with a normal logic gate, and executing the wait for interrupt instruction has no impact on how we drive the RDYIN input. So what remains is how we could extract the wait status outside of the CPU. So let's take a look at the truth table for that. So these are the two pins that we can measure externally. It's what we're inputting into the ready pin, what's the state of the ready pin is. Let's see if we can find a way to figure out the state of the wait signal using only those two signals. So when RDYIN is low, we are telling the CPU to stop ourselves, and so probably we're not waiting. So this should be 1. When RDYIN is low but ready is 1, that's an invalid state because it's not possible. Due to the way we have wired our circuit, as soon as RDYIN goes low, then the ready pin will also go low. So this is invalid. Then when RDYIN is high but the ready pin is low, that's when we are waiting. So this should be 0. And then when both of them are high, then we are not waiting. The CPU is running freely. So this is the truth table. There are two ways we can look at it. So the first one is that the wait signal is the XOR of RDYIN and ready. However, I don't already have an XOR gate in my circuit, and I don't see a use for the 3 other gates that would bring. So I'm going to look at it another way, and we can get the same results by saying that the wait signal is the NAND of RDYIN and the inverse of ready. So both of those statements are valid because this state doesn't exist. Okay, so this is our final circuit. We can see that we now have both the RDYIN and the wait signal unidirectional. When the CPU is waiting internally, the state is reflected at the wait output of the NAND gate. We can see that if we change this to not waiting, then this is reflected externally as well. And if we change the state of our ready input, it doesn't impact the state of the wait signal. So this is all working as it should. The only case where it's not actually possible to determine whether we are in the waiting state is when both the CPU is waiting and we are asking it to wait anyway. In that case, the wait signal would return high, even though the CPU is internally waiting. However, there's no way to determine that, only from the signals that the CPU is giving out. So I think this is good enough. Let's move on to implementing this on a breadboard. Now, before we go and build it, there's the question of which diode I'm going to use to build this circuit. So when we're driving RDYIN high, there's no current going through this diode, and so the ready pin is going to float high using the internal pull-up, and so the diode doesn't matter in this case. But when we pull RDYIN low, then we have to pay attention to the forward voltage of the diode so that the signal at the ready pin remains compatible with our logic. So assuming we drive the RDYIN pin with a gate, so let's look at the datasheet of the 74AC04, for example. It doesn't really matter which gate it is, but the voltage levels are going to be different depending on the family you're using. So assuming an AC family, which is CMOS, the maximum current that the gate can provide is 24 milliamps. And so if we look at the maximum voltage when outputting a low signal at 24 milliamps, assuming we're running at 5 volts, this is 0.44 volts. So at the maximum, when we're driving RDYIN low, there's going to be 0.44 volts here. Then if we think about the inverter that is here, we want this inverter to register a low level. So let's look at the low level input voltage. At 5 volts, it's between maximum 1.35 or 1.65. So let's take 1.35 as an example. For the inverter to register the low level here, the voltage needs to be less than 1.35 volts. And so if we compute the difference, the maximum voltage drop across the diode can be 0.91 volts. If we take a look at the inputs of the CPU at the ready pin, in the datasheet of the CPU, we can see that the input low voltage for the ready pin can be at a maximum 20% of VDD. Now VDD can go from 4.75 to 5.25. So 20% of 4.75 is 0.95 volts. So at a maximum at the ready pin, for the CPU to register the low level, the voltage can be 0.95 volts. So if we compute the difference, then the maximum voltage drop of the diode can be 0.55 volts. So we have to take the minimum of those two and find a diode that has a voltage drop of less than 0.51 volts. So I'm going to use a Schottky diode for this. If we take a look at the datasheet for this family of diodes, we can see that the maximum forward voltage at 1 amp, which is much more than what's going to go across the diode. Remember, we talked about 24 milliamps as a maximum output amperage, is going to be 0.45 for the 1N5817. We know from the datasheets that the voltage increases with the current. So if we're below 1 amp, then it's going to be even less than that. And so we should be pretty good. Okay, so this is our breadboard where we left off the last time. So let's see about adding this new circuit. So we're going to need a new breadboard. I'm going to connect power. So I have here a 74HCT04 inverter and a 1N5817 diode. Let's connect this up. So I'm going to plug the inverter here. I'm going to need a decoupling capacitor. Power connections are getting a bit tight here. Let's connect power and ground. So the ready pin is pin number 2 here on the CPU. So I'm going to bring it over here on the third inverter on the top. Now we need the diode to go from the ready pin to a ready input, and I'm just going to connect it to the pin next to the IC. So this here is going to be our ready input, and this is our ready pin. Now we need to bring the inverted ready pin and RDYIN to the NAND gate here. So let me just remove the pins we tied high. I need to tie all the unused inputs of the inverter high. Base is at a premium here. And at the output of the NAND gate is our wait signal. So in order to test this, I'm just going to add LEDs to the outputs. And so, as I've mentioned in my previous videos, these are LEDs with built-in resistors for 5 volts. Please add a current limiting resistor to LEDs if they don't have them. Now the wait signal is active low, so I'm connecting the anode of the LED to the signal and the cathode to the positive rail. So it should only turn on when we're actually waiting. And actually, let me make this a red LED. And I'm going to add a LED to the wait signal in yellow and also to the wait request signal, also in yellow. So now we should be able to test this. Let's bring in some power. Okay, so I just spent 10 minutes looking for a short that I just did it again when I moved the breadboard. What? Okay, so it turns out that the clock was an input to our circuit and it was left floating. So I had to set a value for the clock, and that stops our short circuit from happening. Okay, so let's resume where we left off. So what I want to do is, first of all, check that the ready pull-up is working, because the LED is lighting up, but I suspect that there's not enough current here for it to light up. Let's check with a voltmeter. This pin here is going to be our ground. Let's see what voltage we have on the ready pin. So it's not floating high by a lot. 1.6 volts. So according to the datasheet, the minimum input high voltage is 80% of VDD. So this is clearly not floating high. But it looks like the inverter is still recognizing this at high input because the output is low. So our input voltage is 4.95, which is within spec. Without the LED, it seems to be a bit better. Ah, okay. Now I understand. By plugging in the LEDs, I was pulling in too much current, and so the pin wasn't strong enough to deliver the current for the LED. All right, so this pull-up seems to be working fine. Let me add an LED on the output of the inverter, which should have enough current. This LED is on when the ready pin is high, and so the output of the inverter is low. Let's see what we can do with our inputs. So if I tie the ready in high, nothing should change. The ready pin is still high, and we're not in the wait state. But if I bring in low, what's going wrong this time? Ah, I'm stupid. I just connected this to the wrong rail. Wasn't doing anything. So let's connect this properly and try again. So if I bring it high, nothing changes, of course. And if I bring it low, then ready becomes low. And we're still not waiting. So the ready in pin is high. If I tie the ready pin to ground to simulate the CPU waiting, we should see this LED lights up. Yep, correct. And the CPU ready pin is low. That's normal. And if I tie ready in low, then we are not waiting anymore because we are stopping the CPU manually. Okay, so this all seems to be working fine. I'm going to leave RDYIN jumpered in high. And I'm also going to leave those two long wires here because in the next video I'm going to add a bunch more ICs to the circuit and so do a bunch more rewiring. So I know these are going to be temporary. I just realized I'm missing a decoupling capacitor here. So this is a 10 microfarad capacitor. I'm putting one in each power rail. Okay, let's go back to KiCad. Okay, so this is our KiCad project where we left off the last time. I'm just going to quickly add the new circuit that we just built. So let's get started. So we don't need a pull-up on the ready pin because it's included in the CPU, but we do need it on the RDYIN pin, which is going to this gate here. So we don't want to leave it floating if we're not using it. Okay, so this is the circuit updated. Okay, so one thing I want to test before calling this circuit done is the speed at which the internal pull-up on the ready pin will pull the pin up once we release the ready input. Indeed, when we drive the pin low, the diode is conducting, and so the ready pin will immediately be brought low. But when we release the input and bring it high, the diode is not letting current pass through. So the speed at which the pin will be pulled up depends on two things. It depends on the stray capacitance of our circuit, and it depends on the strength of the pull-up here. So let's connect our oscilloscope and see if we can characterize this behavior. So I'm going to add a probe on the ready pin in yellow. And then we need to generate a rising edge on the ready input. And for that, you could use a button. But I'm going to use this circuit that I built when I was working on Benito's build. And it's just a clock circuit, so that it's going to generate a square wave, basically, for me. So I'm just using it as a signal generator. So let's connect it. And I'm going to send the square wave over to the RDYIN pin. So we alternatively request the CPU to wait and then release it immediately after. So there it is. And let me add a second probe on the oscilloscope for this input signal. So as you can see, the clock in blue is generating a square wave, and in yellow, our ready pin is responding. But what's interesting is what happens in the transitions. So let me zoom in. Right now, the scale is 2 microseconds per division. And so if I measure, it looks like it takes as long as 5 microseconds for the ready pin to be fully up to 5 volts. So in the datasheet, we know that the input high voltage should be a minimum of 80% of VDD, and VDD can be as low as 475 volts. And so 80% of 475 is 3.8. So we should measure on the y-axis here at 3.8 volts. There you go. And so it looks like the ready pin takes 1.40 microseconds to be pulled up. That's quite high. That's like a few tens clock cycles. And so we probably don't want that. We want the ready pin to respond immediately to the input. What we could do is add another pull-up resistor to the ready pin. Hopefully it will let more current through to VDD and help charging the stray capacitance faster. So let me add a 10K resistor as a pull-up and see what changes. So you can definitely see as I'm touching the circuit and adding capacitance that the ready pin is responding more or less slowly. But when I let it go with the 10K pull-up resistor, you can see it's much faster. So let me zoom in. And now it looks like the ready pin takes 600 nanoseconds to be pulled up. So that's still quite slow. It's still multiple clock cycles. So let's try with a 1K resistor. And that looks much faster. Let me zoom in again. And so now it looks like the ready pin is responding almost immediately. There's a bit of ringing on the line, but it looks like even after the ringing, it's still less than half of a clock cycle at our frequency. So that's much better. So let me unplug the oscilloscope and the clock generator, and we can add this resistor in a more permanent way. There we go. And I'm also missing the pull-up on the ready input. So let me add that now. So that's our circuit completed. Now, of course, adding this external pull-up will increase the current consumption of the CPU in the waiting state. So if you're planning on powering this through a battery, you should probably try to find another circuit. However, I'm not going for the least power consumption here, and so for my purposes, this is going to work. So that's our ready pin taken care of. So the next thing I want to work on is take into account the ready pin in our data bus demultiplexing circuit. There's going to be a bunch of modifications we need to make to the glue logic. However, I think this video is going to be quite long already, so I'm going to split it into 2 parts. And the next video is going to be about integrating ready in the glue logic for a data bus demultiplexing circuit. So I hope you enjoyed this one. Let me know in the comments if you have any questions or feedback. And I hope to see you in the next one. Goodbye.